In distant galaxies, galactic invaders are at work 3 times a day. A strange flash pulsates across our sky, hundreds of times more powerful than all of the world's nuclear weapons combined, but it wasn't made by people. If one of these flashes happens close enough to Earth, it could wipe out all life here. Most people on Earth are unaware of the potential dangers lurking in space. Imagine this: a massive star explodes in our Milky Way galaxy, sending a deadly burst of energy hurtling toward our planet. This is a gamma-ray burst, the biggest explosion since the Big Bang. There are no warning signs, and then it strikes. The radiation heats up the upper atmosphere, causing the ozone layer to overheat. Human beings would be burned to death by radiation, receiving 100 times the lethal dose. As the ozone layer thins, temperatures rise across the globe, triggering storms, tsunamis, and hurricanes. Most life on land and in the water would be incinerated. This may sound like science fiction, but if a gamma-ray burst from 100 light-years away hit Earth, it could happen. Gamma-ray bursts are the brightest explosions in the universe, with immense power, as they are so far away yet still incredibly bright. They release as much energy as the Sun will produce over its entire 10 billion-year lifespan. Given the vast number of stars and planets in the universe, gamma-ray bursts may have wiped out many civilizations. In the 1960s, these mysterious bursts of radiation were first observed. Initially, because gamma-ray bursts are so bright, most scientists thought they originated within our Milky Way galaxy. There were reasons for this assumption. If they were outside the galaxy, their energy would be almost unimaginable. At that time, even the most powerful telescopes couldn't determine their origin or distance, as the bursts lasted only a few seconds before disappearing. However, scientists began to investigate their afterglow. Most space explosions leave a glowing trail that can last for days or weeks. In the late 1990s, satellites equipped with better optics and X-ray monitors finally captured the afterglow of a gamma-ray burst, revealing that these bursts actually came from outside our galaxy, millions or even billions of light-years away. This meant their power was truly astronomical. The brightness of a gamma-ray burst is equivalent to that of 1,000,000 trillion suns. Such an explosion could obliterate all life on Earth. But why do they happen? It is widely believed that a typical gamma-ray burst is caused by the death of a star at least 10 times the mass of the Sun, though such stars are rare. When a massive star dies, it collapses and forms a black hole. Black holes are created when a massive amount of matter shrinks to a point so dense that not even light can escape. However, some of the star's matter resists being sucked into the black hole center, forming a rapidly spinning disk of matter around it. Within seconds, plasma jets shoot out from the poles where the disk spins, unleashing dangerous gamma rays into space. At the same time, the collapsing star explodes in an extreme supernova. Gamma-ray bursts are so bright because they concentrate an enormous amount of energy into a very small area of the sky. Only 1 in every 300 gamma-ray bursts is directed toward us, so we only see a fraction of them. Even if a gamma-ray burst occurred not 100 but 1,000 light-years away, Earth could still be destroyed in a way that resembles the end of the world. If a gamma-ray burst were to occur within 100 light-years of Earth, it would be approximately 500 times brighter than the Sun and would consist of gamma rays. The energy delivered to Earth's upper atmosphere would be equivalent to the detonation of 100,000 megatons of nuclear bombs. This would deplete the ozone layer, cause acid rain, and result in flash burns, incineration of vegetation, and possibly even nuclear-like weather, leading to mass extinctions of species around the globe. On the other side of the Earth, however, there would be a safer place to be, as gamma rays do not penetrate the planet, so people there wouldn't suffer flash burns. However, the consequences of altered atmospheric composition and ozone depletion would eventually affect that side as well. And no one knows exactly what would happen then. This nightmare scenario has a 1 in a trillion probability of occurring once in Earth's history. If you were caught in the beam, it would be a terrible day, as the radiation is so powerful it can break down your molecules. Currently, there is no way to protect humanity from gamma-ray bursts that occur close to Earth. They travel at 186,000 miles per second, or the speed of light, so by the time we detected them, they would have already struck our planet. Gamma-ray bursts could pose a hazard to Earth or any living thing within their range. Astronomers believe gamma-ray bursts might have caused some of Earth's mass extinctions, including the one that occurred 450 million years ago, which wiped out the Ordovician and Silurian species. Creatures near the ocean's surface were hit much harder than those in the deep ocean, consistent with what would happen during a powerful gamma-ray burst. In a galaxy the size of the Milky Way, gamma-ray bursts happen about once every few 100,000 years. According to astronomers, even though they can be extremely destructive, you have to be relatively close to be affected by one. A gamma-ray burst that is close enough to impact life on Earth occurs about once every 5 million years. Since Earth formed 4.6 billion years ago, about 1,000 such events have occurred. So while the chances of a close gamma-ray burst are not zero, they're low enough that you don't need to worry about them unless you plan on living for 5 million years. Humanity has obviously survived past gamma-ray explosions unharmed, but this still shows how far-reaching their effects can be. Fortunately, the threat to Earth from gamma-ray bursts is extremely low. Astronomers have studied all the closest potential gamma-ray bursts, and none of them are close enough or oriented in a way that would cause them to strike Earth. So, what do you think? In our solar system, Earth shines like a sapphire jewel. We go about our daily lives unaware that danger could be coming from deep space. The paths that Earth and most other objects take around the Sun can usually be predicted, and most of the time, things are quiet and peaceful. But sometimes, they become chaotic and violent. Earth can be hit by space rocks, zapped by dangerous space weather, jolted, jostled, and threatened by the energy and forces of cosmic objects. Earth is on a wild ride through space that is often very dangerous. When you're moving fast on a predetermined path, you hope nothing crosses it because there's nothing you can do. Rusty Schweickart, a former astronaut, knows how dangerous space can be. During the Apollo 9 flight in 1969, he was in charge of the lunar module. He is now warning about the risks of an asteroid named Apophis, which is getting dangerously close to Earth. Everyone took notice because the probability of impact was significantly higher than any other risk we had seen before. Schweickart has a frightening real-life example of how devastating even a smaller asteroid than Apophis can be when it hits. On June 30, 1908, at 7:15 a.m., an object the size of a half-football field hurtled through space at about 34,000 miles per hour, leaving a fiery trail behind it. Within minutes, the fireball hit Earth's atmosphere and exploded violently near the Tunguska forest in Siberia. The explosion was the largest ever recorded in Earth's history, splitting the waves and setting fire to 8 million trees over an area larger than half of Rhode Island. Because the explosion occurred in a sparsely populated area, no one was killed directly. But if that asteroid had hit just a few hours later, it would have struck Europe, and if it had exploded over one of Europe's largest cities, 1 million people could have died. For the past 100 years, the Tunguska explosion has been shrouded in controversy. Many researchers now believe an asteroid caused the explosion, though it never actually impacted the ground, instead exploding 5 miles above Siberia's frozen landscape. When it smashed into the lower atmosphere at about 50,000 miles per hour, it was like an egg hitting concrete. The explosion released energy equivalent to 15 megatons of TNT, making it 1,000 times more powerful than the Hiroshima explosion. Over a large city, this would be catastrophic. NEOs, or near-Earth objects, are what scientists call these trespassers. They are comets and asteroids, leftover debris from when the planets formed. The Oort cloud, part of the Kuiper belt that extends past Neptune, is where comets travel. Asteroids take a curved path between Jupiter and Mars, but their orbital journey is not always routine. We don't have to worry too much about asteroids because they generally orbit in a somewhat orderly belt between Mars and Jupiter. However, when one escapes that belt and all its mass and energy is heading towards Earth, that's when astronomers start to get concerned. It's not uncommon for cosmic debris to be jolted out of its orbit and head for Earth. Most of it evaporates in our planet's dense atmosphere, but a larger object can break through and crash to the surface. Asteroids are a real and dangerous threat. If you look to the cosmos for forces that have caused mass extinctions before, it will happen again. About 65 million years ago, an asteroid the size of a small city hurtled down from the sky and exploded in the Yucatan Peninsula near the town of Chicxulub in Mexico with the force of 100 million megatons of TNT. This impact hurled billions of tons of Earth's crust into space, creating a blanket that blocked out sunlight, destroyed the food chain at its roots, and led to the extinction of countless species, including the dinosaurs. We often think of asteroids as catastrophic, but if it weren't for an asteroid, we might not be here today. Our mammal ancestors were merely trying to avoid becoming appetizers for T-Rex. But when T-Rex was wiped out, it opened up an ecological niche that allowed our mammal ancestors to evolve into something more ambitious, leading to the rise of primates, and eventually humans. It's ironic that the same kind of cosmic event that made it possible for humans to exist could one day wipe us out. In 1998, Congress asked NASA to find all near-Earth objects, NEOs, that were at least half a mile across, and what they found was unsettling. More than 850 NEOs are in our vicinity. These asteroids are our closest and most dangerous space neighbors. Tracking these near-Earth objects is a bit like monitoring storms. By observing them day after day, you get a better idea of their path, size, and how fast they would hit Earth if they did. Using telescopic technology, NASA's Space Guard survey has detected over 90% of all harmful near-Earth objects. These frightening entities could strike Earth with more force than all the nuclear weapons in the world combined, potentially triggering a mass extinction. While we wouldn't expect one to hit every few 100,000 or millions of years, if it did, it could wipe out significant portions of the population. These rare events have massive impacts when they occur, affecting the entire planet. An impact wouldn't just devastate a continent with powerful shock waves, the debris would be flung into the air, heating it to 1,000 degrees, and igniting vegetation worldwide. Even smaller objects could cause disasters, which is why Congress has asked NASA to locate all NEOs with a diameter of 500 feet, about the size of the Colosseum in Rome. An object of that size could destroy a city or even a small state. Scientists are most concerned about the asteroids they haven't found yet, rather than the ones they have. At the moment, there are about 2,000 objects that we can't be sure won't hit Earth. However, we now have the technology to prevent near-Earth objects from ever hitting our planet again. We can literally start altering the local solar system to make it safer for life on Earth. The question is whether or not we'll end up like the dinosaurs. It's hard to believe that Earth has been around for more than 4.5 billion years because it's been through so much since its formation. Asteroids continue to enter our orbit and impact our world year after year, much like a boxer taking hit after hit. But one day, Earth could be knocked out. We've learned that near-Earth objects, NEOs, frequently fly by us, and we're becoming increasingly capable of altering our surroundings to help ensure our survival. One such object is a space rock named Apophis. In 2004, this pockmarked rock, about 750 feet across, came close to Earth. It is now scheduled to pass dangerously close to our planet again on Friday, the 13th of April 2029. In 2029, Apophis will come closer to us than our own communication satellites that circle the Earth. If you are in the right place, you will be able to see Apophis pass by Earth with your own eyes. That's how close it will get. You won't even need binoculars. Over 99% of the time, Apophis will miss Earth in 2029. However, if it passes Earth at an exact distance of 18,893 miles, it may pass through a gravitational keyhole, a small area in space that is only half a mile wide. If this happens, Earth's gravity could alter Apophis's path, potentially bringing it back to hit Earth on April 13, 2036, 7 years later. The gravitational effect of Earth could cause Apophis's orbit to expand to precisely the size needed to bring it back around to hit Earth in 2036. Currently, Apophis has a 1 in 45,000 chance of delivering a deadly blow in 2036. It's one thing to say there's a 1 in 45,000 chance that it will hit Earth, but what you really want to know is if there's a 1 in 100, 1 in 10, or 1 in 1 chance that it will hit. We have to consider Apophis the same way we look at any natural disaster. You know the date of the potential impact, where it might happen, and the angle of the orbit, so you can create a map. The potential impact path starts in western Siberia, cuts across the Pacific Ocean near California, goes through Central America, and ends in Western Africa. Scientists have proposed a frightening scenario of where Apophis could strike with a force of more than 1 million megatons of TNT. The asteroid could hit the Pacific Ocean off the coast of California. Such an impact would create a hole in the water 5 miles wide and 9,000 feet deep, causing tsunamis with waves up to 50 feet high to hit the coast, resulting in unimaginable human loss. If a rock 1,000 feet across hits the ocean, it's a serious concern. Scientists are working on ways to prevent such a cosmic strike from happening. One possible plan is to blow up the asteroid, but some worry that this could make the problem worse by sending more pieces of the asteroid our way instead of just one. The new goal for experts is to change the path of asteroids that could hit Earth. By altering its velocity by just a 10,000th of a mile per hour, the asteroid could miss Earth instead of hitting it. If we know about an asteroid far enough in advance, we can change its path. Although a space probe has landed on an asteroid in the past, the most challenging idea is launching a manned mission. Once on the rock, astronauts could mount a radio transponder to track its location. Now, the United Nations plans to draft a treaty to determine who will be responsible for deflecting killer asteroids. If we are so careless as to do nothing even though we know this is going to happen, it will be a real crime. Any asteroid hitting Earth will require an international disaster response. In addition, training is needed in disaster and emergency management institutions and for the public regarding the asteroid threat. It is important that everyone is aware of the level of threats and the potential to eliminate them. Beyond this, amateur astronomers can work together with scientists to defend our planet. They can help identify smaller and potentially destructive asteroids hidden in the universe. So, would you like to be an amateur astronomer? Who knows, maybe you can be one of the guardians of our home. On a night in early September 1859, people all over America could see the aurora. It was blood red and so bright that miners in the Rockies came out of their tunnels thinking the sun was rising. In fact, it was so bright that even at midnight, you could read a newspaper. This didn't just happen in the US, people all over the world saw these auroras. No one knew why they had occurred, but earlier that same day, an astronomer had observed something on the sun's surface that he called a white light flare. Back then, the flare and the aurora seemed unrelated, but we now know that the spectacular aurora was caused by that flare, which was a coronal mass ejection. If such a violent event were to happen again, it could destroy our modern technological world. The sun is the most familiar object in the sky, providing all life on Earth with heat and light. It is so massive that it's hard to imagine, making up 99% of the mass of the solar system. This nearly perfect sphere has a diameter of 1.4 million kilometers and has been burning hydrogen and helium for the last 5 billion years. But from an astronomical point of view, the Sun is nothing special. It's a G-type main sequence star, also known as a yellow dwarf. However, appearances can be deceiving. Solar flares and explosions of plasma particles and radiation from its surface travel far into space, a process we call the solar wind. Solar storms, on the other hand, are much more violent eruptions, and a coronal mass ejection, CME, is the most dangerous because it has the potential to bring our high-tech society to its knees. Today, we'll find out just how bad a CME could be and what astronomers are doing to monitor our star and predict when such events might happen. Let's step back in time to 1859. In Victorian Britain, it was quite acceptable for a gentleman to be interested in solar astronomy, and one man excelled at it, Richard Christopher Carrington. Unfortunately, we don't know what he looked like because no known portraits of him exist. Carrington made several important observations, including the discovery that different latitudes on the Sun rotate at slightly different speeds, indicating that the Sun is not a solid body but a fluid one. He also observed that sunspots could signal the beginning of a solar storm. On Thursday, September 1, 1859, there were no clouds in the sky, so Carrington was doing what he always did, looking for sunspots. Using his telescope to project an image onto a screen, at 11:18 a.m., he saw two brilliant beads of blinding white light appear in what he described as a kind of conflagration. Stranger still, they vanished after 5 minutes without any clear reason. Carrington had witnessed a coronal mass ejection, a massive magnetic explosion. This event threw a huge cloud of charged particles off the Sun's surface. 18 hours later, Earth was hit by an electromagnetic storm, which people later called the Carrington event. At the time, everyone was talking about the beautiful auroras visible all over the world. Although a few telegraph systems went haywire due to power surges, the storm had little effect on everyday life. Keep in mind, though, this was 20 years before the invention of the light bulb. Today, things would be very different. Coronal mass ejections are common, but they vary in size and direction. The question is, what are the chances that something like the Carrington event could happen today, and how would it impact us? So, what's happening on the Sun's surface when we talk about solar wind and space weather? The Sun is composed of magnetic fluid, and as this fluid rotates, it twists and distorts the magnetic field. A twisted magnetic field stores energy, which can lead to eruptions, known as mass ejections. These explosions are massive, sending out 1 billion tons of material at 1 million miles per hour. We want to know where these ejections are headed because if they move toward Earth, they could disrupt the technologies we rely on. A famous example is the 1989 event in Quebec, where some power systems were disrupted for several hours. We've heard about the Carrington event in the 1800s, but what if it happened today? How would it affect us? Think about how much we depend on satellites now, GPS, communication satellites, weather satellites, and even the stock markets are all interconnected. We also have larger power grids and extensive wireless technology, and we don't fully understand how they would react to a powerful solar storm. How likely is it that something like the Carrington event could happen again? We know the Sun is still capable of producing such events. In 2012, there was an event that fortunately did not head toward Earth, but it did pass over one of the spacecraft we use to monitor the solar wind, pushing all the sensors on that spacecraft to their limits. From what we've learned, this event was at least as powerful as the Carrington event, if not more so. It's largely a matter of luck whether a big CME and one headed toward Earth happen at the same time. As for predicting these events, how well can we forecast the Sun's behavior in a week, a month, or a year? Once a CME is detected, we can start making predictions about its size, speed, and, most importantly, its trajectory. All of this sounds frightening, and space weather is indeed a significant concern. The UK government even lists it on the National Risk Register, ranking it as severe as a flu pandemic. Spacecraft designers are working to understand the most extreme conditions in space so they can build equipment to withstand them to some degree. Both NASA and the European Space Agency, ESA, are preparing to send satellites closer to the Sun than ever before. The UK's Met Office Space Weather Operations Centre, which opened in 2014, is one of only 3 places in the world that can predict the Sun's effects on Earth around the clock. So far, the Sun has shown very few sunspots, and the side facing Earth is not expected to produce any significant CMEs in the near future. For now, things seem calm, and spacecraft, satellites, and power supplies should be safe for the foreseeable future. However, the foreseeable future in space weather forecasts is only a few days at best. We still don't know much about CMEs, where they're headed, how big they are, or when they might happen in the future. 2 new solar probes are being sent closer to the Sun than any spacecraft has ever gone. The Parker Solar Probe's mission is to get close enough to the Sun's surface to fly through the source of the most energetic solar particles. The probe will measure the gas and magnetic fields near the Sun to understand why these particles spread out into the rest of the solar system. Meanwhile, ESA's solar orbiter aims to discover how sunspots, flares, and CMEs on the Sun's surface relate to the solar wind. The success of the solar orbiter will be crucial for our understanding of how the Sun works. We believe that the Sun's magnetic field is created in a way similar to Earth's, but it is much more dynamic and constantly changing. There is an 11-year sunspot cycle during which the Sun's magnetic fields move toward the poles, and the polarity reverses. Additionally, the magnetic field extends into the solar system and flows over all the planets. Solar Orbiter will measure these magnetic fields for the first time, and it will also give us the opportunity to observe the magnetic fields as they move toward the Sun's poles. To achieve this, Solar Orbiter will capture images of the Sun's atmosphere and measure the number, speed, and temperature of particles moving through the space between the Sun and Earth. However, the magnetometer, which is designed to measure the tiny magnetic fields in space carried by the solar wind, could be one of the most important and sensitive instruments. The Sun is ever present in our lives. It provides us with light, warmth, and even life itself. For Richard Carrington, who was the first person to record a solar flare, it was just a strange event. But now we know that these events can cause significant damage to our world. With new satellites and more observations, we might be able to learn more about these events and predict when the next coronal mass ejection will occur. In the beginning, nothing existed. After that, the cosmos began to take shape some 13.7 billion years ago. How this happened or whether there was a time before time is still a mystery. Yet, physicists have pieced together an approximate timeline of significant events in the cosmos's existence using telescope data and models of particle physics. From its beginning to its inevitable demise, we examine key points in the evolution of our universe here. The Big Bang. The Big Bang is a moment in time, not a location in space, from which everything else unfolded. To be more precise, it's the first second of time, the point in history from which all other seconds have been measured. Despite its common name, the Big Bang was not an explosion, but rather a time when the universe was incredibly hot and dense before space began to expand outward in all directions simultaneously. The Big Bang scenario suggests that the universe was an infinitesimally small point of infinite density. However, this is merely a convenient way of expressing that we don't know for sure what happened at that time. We now understand that the cosmos breaks down at the Big Bang because mathematical infinities don't make sense in physics equations. Cosmic inflation era. The next cosmic event was the rapid expansion of the universe in size. The universe may have expanded exponentially after the Big Bang, tearing off previously colliding parts of space. This period, known as inflation, is still mostly theoretical, but it has gained favor among cosmologists as a possible explanation for the striking similarity between distant parts of space. Attempts to detect this expansion in light from the early cosmos were reported in 2014, but further investigation revealed that the true culprit was nothing more than interplanetary dust causing interference. Quark-gluon plasma. The temperature of the early cosmos ranged between 7 trillion and 10 trillion degrees Fahrenheit, 4 trillion to 6 trillion degrees Celsius. Just a few milliseconds after the Big Bang, quarks, elementary particles ordinarily contained within protons and neutrons, were free to move about at these temperatures. These quarks combined with gluons, the carriers of the basic force known as the strong force, in a primordial state that pervaded the whole universe. Scientists have replicated these conditions in particle accelerators on Earth, both in terrestrial atom smashers and in the early cosmos. However, this condition only lasted for a few fractions of a second. The early epoch, the period of time beginning a few thousandths of a second after the Big Bang, was marked by intense activity. As the universe expanded, it cooled, creating an environment conducive to the merger of quarks into protons and neutrons. The cosmic neutrino background, which has not yet been detected by scientists, was created 1 second after the Big Bang, when the density of the cosmos decreased enough for neutrinos to travel through space without interacting with anything. The first atoms, protons and neutrons, fused together during the first 3 minutes of the universe's existence, creating the isotope of hydrogen known as deuterium, along with helium and a trace quantity of the next lightest element, lithium. This process stopped as the temperature dropped. As the temperature stabilized 380,000 years after the Big Bang, hydrogen and helium atoms could combine with free electrons to form the first neutral atoms. The cosmic microwave background, a remnant of this era first identified in 1965, was created when photons that had previously collided with electrons were able to travel without being disrupted. The Dark Ages. There was a lengthy period of time when nothing in the cosmos emitted any light. The cosmic Dark Ages refer to this time frame of around 100 million years. Because practically all of what astronomers know about the cosmos can be gleaned by studying starlight, this era remains exceptionally challenging to study. It's difficult to piece together what happened when there are no stars to guide us. The first stars formed when hydrogen and helium began to compress into massive spheres about 180 million years after the Big Bang, creating extreme temperatures at their cores. The intense photons from these early stars and galaxies broke apart neutral hydrogen atoms in interstellar space into protons and electrons, leading the cosmos into a period known as cosmic dawn or reionization. It's hard to set a precise time frame for reionization because it happened so soon after the Big Bang, and its signals have been obscured by subsequent gas and dust. Scientists can only determine that it was likely completed around 500 million years after the Big Bang. Large-scale structures and supermassive black holes developed almost 1 billion years after the Big Bang at the cores of merging early galaxies. Intense quasars, visible from 12 billion light-years away, began emitting bright beams of light. During the universe's middle years, the cosmos underwent further evolution. Denser regions in the early universe attracted more material due to gravity, leading to the formation of a beautiful filamentary cosmic web that expanded into galaxy clusters and long strands of gas and dust. Around 4.5 billion years ago, in one galaxy, a yellow star formed from a cloud of gas, surrounded by rings. These rings eventually accreted into the 8 planets of our solar system, along with numerous comets, asteroids, dwarf planets, and moons. The third planet from the Sun, Earth, retained a lot of water through this process or received it later from comets. Primitive bacteria appeared on Earth between 3.8 and 3.5 billion years ago, evolving into amazing marine creatures and enormous dinosaurs that fed on leaves. About 200,000 years ago, upright beings emerged, capable of contemplating the vastness of space and learning about the universe's origins. This isn't the final chapter, of course. The future of the cosmos remains a mystery to physicists. It depends on our ability to accurately quantify the characteristics of dark energy, the unknown force thought to be accelerating the expansion of the universe. If the universe continues to expand forever, all the stars and galaxies will burn out, and even black holes will evaporate, leaving behind a lifeless cosmos filled with inner energy. Alternatively, the Great Crunch, a reversal of the Big Bang where gravity triumphs over dark energy's expansionary force, could occur. Another possibility is the Great Rip, where the cosmos tears itself apart as dark energy accelerates everything to greater and greater distances. Our solar system is a harsh environment, with destructive volcanoes everywhere, from the ice volcanoes of Saturn's moon Enceladus to the immense lava fields of Jupiter's moon Io, and even on Earth itself. It's truly true that we wouldn't be here if there were no volcanoes. Volcanoes influence and alter our climate. They are both creators and destroyers of life. Today's spacecraft and observatories have revealed volcanoes on planets we once believed to be dead. The discovery of volcanoes on an object smaller than the Moon was a major surprise. If there are volcanoes on other worlds, could there also be life? Volcanoes are among the most powerful natural occurrences on Earth. They create new land, destroy the old, and emit gases that alter the atmosphere we breathe. Deep in our oceans, volcanic heat fuels bizarre new forms of life. Volcanoes help sustain life on Earth, and now we look for signs of life on other planets. We know that life requires water, and we know it requires energy, which is where volcanoes come in, generating tremendous amounts of energy. If we find volcanoes on other planets, we may discover life. The search begins with the planet that orbits closest to Earth, Venus, a planet that closely resembles our own. Venus and Earth have similar masses. About 3 billion years ago, Earth and Venus were very similar, with new land, new oceans, and an atmosphere conducive to life. However, something went wrong on Venus. Something caused the history of Venus to diverge drastically from that of Earth. Venus took a definite turn to the dark side a long time ago, becoming our malevolent twin planet. Today, the surface of Venus is like a furnace, with temperatures reaching 900 degrees Fahrenheit, hot enough to melt some metals, so you wouldn't stand a chance. Venus is a greenhouse world. Its atmosphere contains a high concentration of carbon dioxide, which absorbs solar heat like a blanket. Actual images of Venus's surface reveal a desolate, extremely hot wasteland annihilated by a dense CO2 atmosphere. This CO2 was produced by volcanoes. Spacecraft in orbit provided the initial clues. Radar pierced through Venus's thick clouds and showed volcanic formations all over the planet. These formations resemble Earth's shield volcanoes, round and flat. Shield volcanoes are named for their shape and are known to ooze lava, sometimes for thousands of years. Once we were able to map the entire surface of Venus using cloud-penetrating radar, we began to examine its landforms and discovered many that were quite familiar. In particular, we observed enormous shield volcanoes that resembled the ones in Hawaii. The radar images of Venus were strikingly similar to those of Hawaii's shield volcanoes. In the past, Venus was home to volcanoes. We were astounded when we first saw images of Venus's surface, which revealed a cratered volcanic landscape. There are at least 1,000 large volcanoes and possibly tens or hundreds of thousands of smaller ones. Lava plains cover 3/4 of Venus's surface, evidence of an ancient catastrophe. This could have been a home for life, but instead, it was consumed by flames. Venus's volcanoes expelled trillions of tons of carbon dioxide into the planet's atmosphere, causing temperatures to skyrocket and the oceans to evaporate. On Earth, carbon dioxide can be absorbed into rocks or by the oceans, but on Venus, there is no water, and the temperature is so high that carbon dioxide cannot combine with minerals. Volcanoes released carbon dioxide into the atmosphere eons ago, and as time passed, fewer and fewer methods existed to remove it. Volcanoes effectively sterilized the entire planet. If Venus ever supported life, it is now a barren world. Earth is the only known planet with life, but that may change. The gas giant Jupiter, with its moons believed to be frozen and lifeless, presents a mystery. A cloud hovers over this cold, lifeless world. Upon closer inspection, it was discovered that volcanoes had transformed Venus, a planet once similar to Earth, into a hyperheated inferno. While volcanoes on a planet similar to Earth weren't surprising. The discovery of volcanoes on a moon was astonishing. In March 1979, the Voyager 1 spacecraft provided us with our first up-close look at Jupiter's tiny moon, Io, a world we once believed to be frozen and lifeless. But they witnessed something unusual. They observed an arc next to the moon that almost looked like a second moon behind it. We scratched our heads, wondering what it could be. Everyone knew that Io was lifeless, dull, and uninteresting. Then people realized, oh my god, it's a volcanic eruption. We discovered that Io is engulfed in volcanoes and is geologically extremely active, with constant volcanic eruptions. These eruptions release a great deal of sulfur, which changes color as its temperature changes. It can be red, orange, yellow, or even black. As a result, images of Io's surface resemble a pizza with various types of cheese and olives where the small black spots are. Io is not dead, it is alive and growing, with more than 400 active volcanoes. The largest plume, Pele, erupts from a gigantic lava lake, extending approximately 400 kilometers into space. It would be an extraordinary sight to stand on the edge of that lava lake and observe the plume shooting off into the void of space. Pele's eruptions are so massive due to Io's small size, there's nothing holding the lava back, as there is virtually no atmosphere and little gravity. These enormous eruptions make Earth's volcanoes resemble fireworks in comparison. How can a moon so small be so volcanic? The answer is Jupiter. Just as the moon raises tides in Earth's oceans, Jupiter raises solid rock tides on Io. Io's orbit around Jupiter is not circular, sometimes it's closer, sometimes farther away. Jupiter exerts a gravitational force on Io, stretching and squeezing it every 2 days. The ground rises and falls by nearly 300 feet, generating extreme heat and enormous pressure. Wherever there are weak spots in the crust, lava erupts. Volcanism on Io is therefore planet-wide, unlike on Earth where certain portions are active around tectonic plates or weak areas. Io, however, is an entire moon that acts as one massive active hotspot. It is the most volcanically active body in the solar system, thanks to the immense power of Jupiter's gravity. Volcanic activity on Io has taught us something new. It has shown that internal energy sources can drive volcanism in a way that is distinct from Earth. Io is a world of lava, extremely hot and violent, making it hard to imagine anything surviving there. We have discovered strange volcanic eruptions on numerous planets and moons, but so far, the only world where volcanoes are linked to life is our own, at least, that's what we thought. Then there's Europa, another moon orbiting Jupiter, almost 500 million miles from the Sun. Europa is a 2,000-mile wide sphere of ice. From a distance, its surface appears smooth and polished, but up close, it's a different story. Europa, like Io, is subjected to the immense gravitational pull of Jupiter, which causes its surface to rise in bands, forming ridges and deep fissures. When we first obtained close-up images of Europa, they seemed vaguely familiar, resembling Arctic ice flows on Earth. It turns out they are similar because a global liquid ocean lies beneath Europa's several-mile-thick icy crust. Magnetic measurements suggest that Europa's ocean is an astounding 60 miles deep. Jupiter's gravitational impact heats Europa's rocky interior, possibly melting the ice above as the core is stretched by tidal forces. It's not far-fetched to believe there is a boundary between a hot core and a liquid water ocean. On Earth, underwater volcanic eruptions are surrounded by life, and the same could be true on Europa. Despite the complete darkness, crushing pressure of 2,000 Earth atmospheres, and harsh environment, it could be a cradle for life. If there is life on Earth under such extreme conditions, why not on Europa? Europa has the essential ingredients: an energy source, volcanic activity, liquid water as a universal solvent, and complex hydrocarbon chemistry. Life on Europa would be difficult, but not impossible. On Earth, life exists in searing heat, crushing pressure, and absolute darkness. Life on Europa might resemble our own in unexpected ways. If life exists beneath Europa's ice, it would likely be aquatic, lacking eyes due to the absence of light, and would probably use sonar to navigate its surroundings. Volcanoes on Europa could be the genesis of new life. It's even conceivable that Europa is typical, that this is the norm for planets with life, while Earth may represent an exception. Consider that Europa could serve as a model for billions of moons in the universe with liquid oceans. This perspective suddenly expands our horizon several billion times. By looking at the moons of Jupiter, we realize our solar system alone is home to over 170 moons. Multiply this by the size of the universe, and that's a vast number of potential habitats for life. All that's required is liquid water and a source of energy, potentially provided by volcanoes, which are ubiquitous. Take Saturn, for example, which is twice as far from the Sun as Jupiter but also has volcanic moons. Similar to Europa, these moons could potentially support life. Saturn is one of the oddest planets in our solar system, with a ring system 600,000 miles wide and an astounding 62 moons, one of which holds a secret, Enceladus. Enceladus is one of Saturn's smaller and more distant moons. It has long been known to be covered in ice due to its extremely bright and reflective surface. However, when the Cassini spacecraft visited Saturn, it made a remarkable discovery, not on Saturn itself, but on Enceladus. The Cassini probe revealed a massive plume, backlit by the Sun, erupting into space, conclusive evidence of volcanic activity. Cassini's sensors zoomed in on the Moon's south pole to capture enormous craters scarring its surface. At Enceladus's south pole, there are extraordinarily large fissures that open and close as the Moon orbits Saturn, influenced by tidal forces. These fissures are enormous, extending for hundreds of kilometers. And when they begin to open, you would see a large crevasse opening at approximately 100 miles per hour along its length, an incredibly spectacular sight. Huge gravitational forces cause the surface to open and contract with incredible velocity. This helps produce the heat necessary to melt ice and form oceans beneath the surface. The conditions of the water beneath the surface of Enceladus are ideal for life. It is at the perfect temperature and would be beneficial for sustaining life. The liquid water would be just like seawater here on Earth, and the chemistry of the water we observe erupting from these fissures suggests that it contains salt and organic matter as well. Therefore, we have identified a location in the solar system where there is a strong possibility of life right now. In the ice particles, Cassini has detected complex carbon molecules in conjunction with liquid water, suggesting that life could potentially exist deep within this mysterious moon. Enceladus may not be alone in this regard. Another of Saturn's moons, Titan, might also harbor life. Titan is one of the largest moons in our solar system and the only moon with a thick atmosphere. It is a frozen world, with ice as hard as rock and lakes of liquid methane. Yet, we may also discover evidence of volcanoes and the tantalizing possibility of extraterrestrial life on this moon. Volcanoes are one of the most destructive forces in the universe, as evidenced by Io's raging eruptions and Triton's ice and nitrogen explosions. However, even on Saturn's enigmatic moon Titan, destruction can lead to the prospect of life. Titan has a diameter of 3,000 miles, making it larger than Mercury, and it has the thickest atmosphere of any moon in our solar system. There is weather, including cyclones, winds, rain, and even lakes, but the temperature is so low that liquid methane replaces water, and it is loaded with essential compounds for life. Titan has proven to be one of the most fascinating locations in the solar system. It's an active world and the only moon with a dense atmosphere, which is very similar to Earth's due to the presence of nitrogen and organic molecules. High in Titan's atmosphere, methane gas reacts with sunlight to produce compounds essential to life. But if sunlight consistently converts methane into organic compounds, why does the methane not run out? Methane is abundant in the atmosphere, but we know that it is quickly eliminated by sunlight, so it shouldn't be there. There must be a source of methane. Something on Titan emits methane in a continuous stream. Cassini has spotted what appears to be a crater, and infrared cameras reveal that the crater is surrounded by various types of materials. Scientists believe the green areas may be volcanic, possibly plains of lava ejected from Titan's interior. On Titan, the boiling liquid emitted by volcanoes could be either ammonia or water. Methane and ethane are emitted by Titan's volcanoes, and this is likely the cause of the planet's extremely dense cloud cover and orange atmosphere. This atmosphere likely originated from the outgassing of Titan's volcanoes. Even on a globe as rigid as Titan, volcanoes require heat. On Titan, there are two sources of heat. Radioactive substances heat the interior, and Saturn's enormous gravity affects the Moon, similar to Enceladus. These two forces produce sufficient heat to transform ice into water and liquid methane into gas. Could volcanoes on Titan give life a chance to survive there? The chemical reactions necessary for life as we know it require an atmosphere, a solid surface, liquid water, and heat. Volcanoes could provide all of these on Titan. If life does exist on Titan, it would be truly alien. It might breathe hydrogen instead of oxygen and possibly swim through methane reservoirs at 300 degrees below zero. There may be oceans of ethane, possibly tidal pools, as well as volcanic and hydrothermal activity. Perhaps volcanic heat could produce enough energy to support life on Titan. That's speculation, but it can't be ruled out. However, we may not need to travel so far to discover signs of life. We may find it on Mars, a volcanically active world much closer to home. Volcanoes are ubiquitous throughout the solar system. Planets such as Io, Titan, and Triton are intricate, volatile, and violent. Once we believed that Earth was the only planet with both volcanoes and life. Now we find volcanoes everywhere, but alien life has yet to be discovered. Volcanoes exemplify the absolute force of creation and destruction. They go hand in hand. It is literally true that if there weren't volcanoes here, we would not be here either. Volcanic cauldrons are the birthplace of life. Volcanoes create new landscapes, seed the atmosphere with complex chemicals, and replace the old with the new. If volcanoes are linked to the processes of life, where is life on other planets? Perhaps the origin of the answer lies in ancient times when the solar system was immature, on a planet similar to our own. This is the planet Mars. 3 billion years ago, volcanoes were active, and the greatest volcano in the solar system still stands. The cliffs leading up to it are more than 6 miles high. Even Mount Everest would be dwarfed in their shadow. This is the formidable Olympus Mons. It covers an area the size of Arizona, and its crater alone is 53 miles wide. A structure of this magnitude takes millions of years to construct, a period of time that volcanoes on Earth never have. The Earth's crust is constantly in motion. In the depths of the Earth, a solitary hotspot forces magma to the surface, creating a new volcanic island. While the hotspot remains stationary, the surface is in motion. The new island moves away from the hotspot and is replaced by another volcanic island. Mars is different. The crust is locked solid on Mars. There is simply no tectonic activity. The crust is one big solid plate. So, if there's a hotspot, it just sits there, building and building, resulting in a larger and larger volcano. That's why Olympus Mons is so enormous. Today, Olympus Mons is an icy remnant of a distant, warmer era. Olympus, an extinct volcano on a fading planet, is now a colossal relic. Due to Mars's diminished atmosphere, the ancient volcanic terrain of Mars could one day support life. The evidence is readily available on Earth. Volcanoes in Hawaii have formed enigmatic tunnels known as lava tubes, created when rivers of molten rock rush into the ocean. Lava tunnels are formed when there is an underground river of basaltic lava, magma, and molten rock at 2000 degrees Fahrenheit. Imagine it as an icy river with a crust of ice forming on the surface. It's the same, except here, the crust is solid rock, and the river continues to flow beneath, creating a cave. Recent images imply that Mars's volcanoes may have also created lava tubes. Any rocky planet with basaltic volcanism will likely contain lava pipelines. Now, after possibly millions of years of inactivity, these lava tunnels could revive life on the red planet. This existence could be our own. Radiation will be one of the obstacles that future humans will face when attempting to live on Mars, especially during solar storms. The tunnels and caverns of Mars's extinct volcanoes could one day serve as an ideal home, retaining air and shielding us from harmful radiation. A long-dead volcano could help fill a world with new life. Volcanoes are capable of both destruction and creation. We used to only know about the planets that circled our sun, but now we know that there are rocky worlds and huge gas giants that circle other stars. They have a great story to tell. The early history of these planets would have been very, very violent. Planets are made the same way everywhere. They come from the dust and other materials left over after stars are born. So, if they're all made the same way, what makes them so different? As it turns out, the universe is full of galaxies, gas clouds, stars, and planets. There are 8 worlds in our solar system, but now we know that they are just a small part of the huge family of planets in the sky. It's a very important moment in the history of science to be certain that there are other planetary systems out there. In our Milky Way galaxy, which contains 200 billion stars, there are probably dozens of planets. NASA sent the Kepler Space Telescope into space in 2009 on a 6-year mission to find new planets that orbit other stars. So far, it has found more than 400. Some of these are huge, spinning balls of gas that are 5 times as big as Jupiter. Others are large, rocky worlds many times larger than Earth. Some follow wild, erratic orbits, so close to their star that they are burning up. One thing is clear, no 2 planets are the same, each one is unique. But most of these new worlds are very far away and hard to study. Most of what we know about how planets work comes from the 8 planets that orbit our Sun. Our own planets come in 2 main types. There are 4 rocky planets in the inner solar system: Mercury, Venus, Earth, and Mars, and in the outer solar system, there are 4 giant gas planets: Jupiter, Saturn, Uranus, and Neptune. Each of the 8 worlds is very different from the other 7. When our solar system was born 4.6 billion years ago, the planets began to develop their own personalities. When the Sun ignited, it released a massive cloud of gas and dust into space. All 8 planets, including the metal-rich planets closer to the Sun and the gas planets farther away, came from this cloud of space debris. All the worlds in our solar system are made of the same materials. They're formed from the same cloud of gas and dust but under very different conditions. Some of them formed close to the Sun, where it was much hotter, and some formed far away, where it was much colder. Since the conditions were so different, the planets that emerged were also different. At the beginning of the solar system, there was a pretty even mix of silicates, water vapor, hydrogen, lots of hydrogen, methane, and other elements. These elements in the dust cloud are like ingredients in a cake. They cook in different ways based on how the ingredients are mixed and how hot the oven is. You mix the ingredients, just like with a cake, then put them in the oven to bake, and they change. This is basically what happened in the solar system. The planets cooked in slightly different ways depending on how close they were to the Sun. Near the Sun, where it is hot, gases burn off, and water boils away. Only materials that stay solid at high temperatures, like metals and rocks, can survive. This is why only rocky planets form close to the Sun. As a planet moves farther away from the Sun, it cooks in a different way. But the type of planets that form depends on what's in the cloud. Depending on the composition of the cloud a solar system forms in, it might not have any rocky planets because there wasn't enough material to make something like Earth. Instead, it might have more gas giants or none at all. If you want planets made of rock, you need a cloud full of metals and rocks. The next step is to turn down the heat. As it cools, some of the materials with high boiling point start to condense into solids, forming very small mineral grains. These tiny pieces of rock and minerals are the beginnings of a new rocky world. They start to stick together over time. If you had one dust molecule and another dust molecule, they would collide and form a slightly bigger dust molecule. And they keep getting larger. This process is called accretion. As these things get bigger, they basically become rocks. Then, rocks collide with other rocks to form boulders, and boulders smash together to form larger boulders. At some point, you have something big enough that its gravity is strong enough to start pulling things towards it. Instead of just colliding and getting bigger, it actively pulls in more material. At first, there were a lot of young planets in our own solar system, maybe 100. Most of them didn't make it. If you go to the asteroid belt and look at the asteroid Vesta, you can get a good idea of how large a rocky planet has to be before it can pull itself into a spherical shape. Vesta is only 329 miles across, which isn't quite big enough to be a sphere. To become round, a growing planet needs to be 500 miles across, then it has enough gravity to crush itself into a sphere. Any smaller, and it stays in an irregular shape. Every time a baby planet crashes into something, it gets hotter and hotter until it starts to melt. Gravity then begins to sort the heavy materials from the lighter ones. The lighter materials tend to float up and form a crusty layer, while heavier ones, like most metals, sink down and form a much denser core at the planet's center. Finally, the young planets begin to look like planets, but they still have to survive a time of violence and destruction, a cruel time that will decide which planets will live and which will die. After the Sun formed, all 8 of our planets came from the same cloud of dust and gas, but they turned out to be very different. There was no specific plan for how each of the new planets should form. They did follow the rules of physics and chemistry, but most of what happened was just a matter of luck. About 4.5 billion years ago, our Sun was surrounded by about 100 young planets. It turned into a demolition derby, with planets colliding with other planets, and most of them were destroyed. The early history of these planets was very violent, with many collisions happening during the last stages of each planet's growth. As these collisions occurred, some of the planetesimals began to grow at the expense of others, and the ones that would eventually become planets grew larger, sucking up all the smaller planetesimals around them. This caused a lot of space debris to hit the surface of the protoplanets. In the end, only 4 different rocky planets remained. The events that each planet experienced in the past made them all so different from each other. Mars is a frozen wasteland, Earth flows with liquid water, Venus is a place full of volcanoes, and Mercury is small, barren, and extremely hot. For example, Mercury has a very thin crust and is very dense, which suggests it may have been a larger planet in the past. Then something likely hit it at an angle, stripping off the lighter crust and leaving only the dense core. Earth was also struck hard at the end of its development. It was hit by another body, which tore apart its mantle and sent pieces into orbit around the Earth, where they coalesced to form the Moon. Something similar seems to have happened to Mars. The crust of Mars is thinner in the north than in the south. One theory is that the northern hemisphere of Mars was struck by something early in the planet's history, blowing off much of its crust, which then started to accumulate again in the south. These collisions had 2 effects. They reduced the number of surviving baby planets, and they brought more material to the survivors. For example, if a collision occurred with something rich in metal, those chunks would tend to sink down into what was becoming the core. If the collision was with something light or icy, those materials would tend to float and become part of the crust. Near the Sun, there were 4 rocky planets that were almost fully formed. They were made of a solid core of hot iron, surrounded by a layer of liquid iron, with a shell of molten rock on top, and a crust on the surface. All of these rocky planets were made the same way, from the same basic materials. But each of them turned out very differently, different sizes and different destinies. Space may look empty, but it's not. It's full of stuff blown out from the Sun. Strong magnetic fields are generated by the Sun, rising up in giant loops above its surface. When these fields collide, they release a storm of extremely hot, highly charged particles into space, known as the solar wind. Astronauts can see it from space, but only when they close their eyes. When you close your eyes, you sometimes see a little flash, and that flash is caused by an energetic particle passing through your head and interacting with the fluid in your eye. You might see one of these flashes every few minutes. The solar wind could be deadly to astronauts if they were exposed to a large amount of it. During the Apollo program, there was an explosion on the Sun between two moon missions that would have killed the astronauts if they had been there. Radiation in space is a serious concern, but here on Earth, the solar wind doesn't pose much of a threat because we are protected by an invisible magnetic field generated from the center of the Earth. Magnetic fields can be created by motion, converting kinetic energy into magnetic energy. Deep inside the Earth, the same process occurs. As the Earth spins, the hot liquid metal flows around the solid core, converting its energy into a magnetic field that emerges from the poles. This field keeps the solar wind from entering the planet's atmosphere, protecting everything on the surface. If a planet has a magnetic field, it will divert the solar wind around it. The Earth's magnetic field pushes the solar wind away, shielding our atmosphere and all life on the surface. Sometimes, large storms of solar radiation can disturb the magnetic field, creating spectacular light shows called auroras over the poles. Without a magnetic force field, Earth's atmosphere and water would be blown away by the solar wind, leaving the planet dead and dry, much like Mars. Mars was formed in the same way as Earth, but today it's cold, dry, and mostly inactive. So why have the two planets changed so much? In 2004, NASA sent two robots to Mars, the Spirit and Opportunity rovers, to investigate the planet. They explored miles of Mars' surface and confirmed that it is a dry, dangerous desert with an atmosphere only 1% as thick as Earth's. However, they did find evidence that water once existed there. Mars wasn't always a dry, barren place. There is strong evidence that water once rose from below the surface, flowed across it, and then evaporated. In some places, ripples formed by flowing water can still be seen in the sand. So, not only was there water beneath the ground, but it also flowed across the surface. If Mars once had water, it likely also had a thicker atmosphere. So, what happened? We know that there were once volcanoes on Mars, indicating that the planet had a hot interior at some point. Because Mars was made of similar materials as Earth, it would have had a hot iron core surrounded by liquid metal. This should have generated a magnetic field, but where did it go? Early in Mars' history, the planet likely had a strong magnetic field, possibly generated in the same way as Earth's. However, Mars is smaller than Earth, which means it loses heat more quickly. As a result, its liquid core may have solidified over time. When the core freezes completely, convection stops, the flow of liquid metal ceases, and the magnetic field disappears. Once the magnetic shield stopped working, the solar wind blew away the atmosphere, and the water evaporated. Mars became a cold, empty planet. The rocky planets, Mars, Earth, Venus, and Mercury, all formed within 150 million miles of the Sun. But 4 times farther out, the Sun created a very different kind of planet. These giants are enormous, made mostly of gas, and have no solid surfaces at all. So far, astronomers have discovered more than 400 new planets in distant solar systems, and almost all of them are massive and made of gas. Our solar system has 4 of these so-called gas giants, Jupiter, Saturn, Uranus, and Neptune, all of which have thick, dense atmospheres containing hydrogen, helium, and methane. Why are these outer planets made of gas while the inner ones are rocky? It's much colder out here, 500 million miles from the Sun. At the start of the solar system, there was some dust but mostly gas and water frozen into ice grains. It was cold enough to form solid snow where the giant planets began to form. We believe that ice snowflakes were able to stick together and form the cores of these giant planets. This may explain why the giant planets grew so large. There was so much ice and gas available. Their cores grew to be about 10 times the size of Earth, generating a lot of gravity. This gravity was strong enough to pull in all the surrounding gas, creating thick, dense atmospheres that extend tens of thousands of miles. The more gravity they generated, the bigger they grew, pulling in more and more dust and debris, which formed their moons. Each of Jupiter and Saturn's moons has more than 60 moons. The gas planets have another unique feature: rings. Saturn stands out because of its beautiful rings, but Jupiter, Uranus, and Neptune also have rings, though they are faint and difficult to detect. All four gas giants have rings, but Saturn's are the most prominent. From a distance, Saturn's rings appear to be a single flat disk, but in reality, they consist of thousands of smaller rings, each only a few miles wide. When the Cassini probe flew by, it discovered that billions of pieces of ice and space debris were moving around inside the rings at speeds of up to 50,000 miles per hour. These pieces of ice and rock constantly collide with each other. Some of them form small moons, while others break apart. However, they never grow larger because Saturn's immense gravity pulls them apart. Scientists are just now beginning to understand how the rings came to be. The prevailing theory is that a comet struck one of Saturn's moons, knocking it out of its orbit and bringing it closer to the planet. Saturn's gravity then tore the moon to pieces, and the resulting debris became trapped in rings that now circle the planet. But the true mysteries of the gas giants lie deep within them, tens of thousands of miles below the clouds. This is where things get truly extreme, defying natural laws. Most of the new planets we find orbiting distant stars are enormous gas planets, so large that Jupiter seems small by comparison. Yet, no one knows what happens inside these gas giants, whether they are in our solar system or far away. We do know that Jupiter's thick atmosphere extends 40,000 miles downward, with bands of gas moving at high speeds, creating violent storms on its surface. However, what happens deep inside remains a mystery. To uncover more, NASA sent the Galileo spacecraft on a 14-year journey to Jupiter. On December 7, 1995, Galileo released a probe into Jupiter's atmosphere at a speed of 160,000 miles per hour. As it descended through the thick air, a parachute slowed it down. The probe observed lightning in the clouds and winds reaching 450 miles per hour, transmitting data back to Earth for 58 minutes. What happened to the Galileo probe that we dropped into Jupiter? It didn't hit anything, it just kept falling deeper into Jupiter's environment, with the pressure continuously increasing. The probe measured pressures 23 times higher than those on Earth, and temperatures over 300 degrees hotter. In the environment of a gas giant, as you descend deeper into this soup of hydrogen, which has no solid surface, the material becomes increasingly dense. Eventually, the immense pressure crushes anything within it. Although the probe only made it 124 miles down before being crushed, it provided scientists with a glimpse of what the inside of Jupiter might be like. Yet, the planet's dark core remains a mystery. Like some rocky planets, the gas giants also have magnetic fields. Jupiter's magnetic field is 20,000 times stronger than Earth's and so vast that it extends all the way to Saturn, over 400 million miles away. Just as on Earth, Jupiter's magnetic field shields its atmosphere from the solar wind, protecting it. When scientists studied Jupiter's magnetic field, they discovered that it also affects Jupiter's moons. The volcanic moon Io, which orbits only 217,000 miles from the planet, spews a ton of gas and dust into space every second. This activity is intensified by Jupiter's magnetic field, creating powerful radiation belts and making the region around Jupiter very dynamic. If you point a radio antenna at Jupiter, you can hear how the planets and the magnetic field interact. Jupiter and Saturn can produce auroras without the solar wind. They generate their own magnetic fields due to their immense size. These auroras show that gas planets also have magnetic fields. But how are magnetic fields generated in gas planets? On Earth, this is accomplished by very hot liquid metal spinning around the planet's solid iron core. Gas planets likely have a similar mechanism, but they don't have iron cores that get very hot. Instead, they formed around frozen cores of dust and ice, so we're uncertain about the processes inside them. We don't really know what the deepest parts of Jupiter's interior are made of. It's possible that Jupiter has a solid core at its center, or it might still be liquid. We might never know for sure. No probe could survive the journey 44,000 miles down to the planet's center. The Galileo spacecraft was destroyed before it could reach the center of the planet. Gravity and heat shape how planets evolve. From their inner cores to their outer atmospheres, they're the great creative forces in planet building. But there's one more thing that has a significant impact on how planets turn out, and that ingredient is water. Planets may seem fixed and unchanging, but they are always in a state of change. One planet in our solar system lost its atmosphere and became a desert. Another planet got too hot and turned into a planet from hell. Planet Earth has also undergone changes, and it was water that made the difference. When you look at Earth from space, you see a lot of water. We are, after all, the blue planet. That must mean it's very wet, right? At first glance, our world appears to have a lot of water. After all, 3/4 of it is covered by oceans. But that's not entirely true. Only 0.06% of Earth's mass is water. Some of it is on the surface as oceans, and some is trapped in minerals, but in reality, Earth is a relatively dry rock. All of the inner rocky planets formed close to the Sun. So they started off dry. Any water they might have had either evaporated or was blown away in massive collisions. The formation of Earth was so energetic that if there had been any water, it would have evaporated and left the planet. So where did all the new water on Earth come from? When you look at Jupiter, Saturn, Uranus, and Neptune, you see they have a lot of water locked up inside them. Even more dramatically, at least half of the water on the moons of Jupiter, Saturn, Uranus, and Neptune is also present. A lot of water was out there in the outer solar system. So, how did some of it end up on Earth? The answer almost certainly lies in the fact that some asteroids and comets in our solar system were far enough from the Sun to retain their water. There were millions of these water-rich asteroids and comets that ventured into the inner solar system, and some of them crashed into our planet. Over time, Earth acquired the water that used to be in those asteroids. This is what now makes up the mass of water that covers most of the Earth. Without surface water, there would have been no life. But what if there was too much water? The oceans would be much deeper, covering the continents and even Mount Everest. It's likely that the exact amount of water Earth has is what made it possible for Homo sapiens to evolve into a technological species. About 4 billion years ago, a blizzard of comets and asteroids brought just the right amount of water to Earth, shaping the world we know today. It's possible that the same process is happening somewhere else in the universe right now. There is a lot of water out there, and that much is certain. The most common atom in the universe is hydrogen, and oxygen is one of the next most common. H2O is likely a very common molecule, which is exactly what's happening in our universe. So, water is everywhere in the universe, and we're finding that planets are, too. But we haven't yet found another planet where water exists in liquid form. Scientists have discovered more than 400 new planets, but none of them resemble our world. What we haven't found yet is a planet around another star that is about the same size, mass, and chemical makeup as Earth. It remains an extraordinary goal for humanity to find other places that remind us of home. But we'll keep looking. We know our galaxy alone has around 200 billion stars, and up to 40 billion of them could have their own planets. We are entering what will be called the golden age of planetary exploration in the future. We'll start to really understand, for the first time, how different things are out there. I think this is going to be a very exciting time. The laws of physics and chemistry tell us how planets are made. Many scientists believe it's only a matter of time before we find another planet like Earth, one that formed from the same materials, in the right place, with the right amount of water. One thing is certain, there are billions of planets out there waiting to be discovered. Ladies and gentlemen, welcome to today's topic, aliens. Are they real? Do they exist? And if so, what do they look like? Today, we will dive deep into the topic of aliens, exploring various theories and facts about these mysterious creatures. Extraterrestrial life exists. This is the theory that life exists elsewhere in the universe, perhaps even within our own solar system. Microbial life could potentially exist on Mars or some of the moons of Jupiter and Saturn, for example. More complex life forms, such as intelligent civilizations, could also exist on planets orbiting other stars. The Fermi paradox. The Fermi paradox suggests that if intelligent life is common in the universe, why haven't we detected any evidence of it? Some theories suggest that intelligent civilizations tend to self-destruct, while others propose that they are too far away or have no desire to communicate with us. Ancient aliens. This theory suggests that aliens have visited Earth in the past and have influenced human history and culture. Proponents of this theory point to ancient artwork and texts as evidence of alien visitation. UFO sightings, unidentified flying objects, UFOs, are often cited as evidence of alien visitation. While many sightings can be explained by natural phenomena or human-made objects, some remain unexplained and could potentially be evidence of extraterrestrial visitation. The simulation theory. This theory proposes that our entire reality is a computer simulation created by an advanced civilization. While not specifically about aliens, this theory suggests that the creators of the simulation could potentially be an extraterrestrial civilization. To start with, let's address the most basic question: do aliens exist? Well, according to the Drake equation, developed in 1961 by astronomer Frank Drake, the probability of intelligent life existing elsewhere in the universe is high. The equation takes into account factors such as the number of stars in our galaxy, the number of planets that could potentially support life, and the probability of life forming on those planets. Using these factors, the Drake equation estimates that there could be millions of intelligent civilizations in our galaxy alone. But the question remains, have we ever encountered these civilizations? Many people believe that we have, and there are countless stories of alien sightings, abductions, and encounters. However, there is little concrete evidence to support these claims. So, let's explore some of the most popular theories about what aliens might look like. The traditional image of aliens as small, green, big-eyed beings is a product of popular culture. However, it is unlikely that aliens would look anything like this. In fact, it is impossible to predict what aliens might look like, as their appearance would depend on the conditions of the planet they evolved on. For example, if an alien species evolved on a planet with high gravity, they might have shorter, stockier bodies. If they evolved on a planet with a harsh, radiation-filled environment, they might have evolved to be more resilient to radiation. It's also possible that some alien species might not even have bodies as we know them. They might exist as pure energy or as a hive mind collective. But why would aliens visit Earth? There are a few possible reasons. Some scientists speculate that aliens might be interested in our planet because of its unique location in the universe. Earth is in a Goldilocks zone. It's not too hot, not too cold, and has the right conditions for life to thrive. Aliens might be interested in studying our planet to learn more about how life can survive in these conditions. Another reason aliens might visit Earth is to make contact with us. If there are millions of intelligent civilizations in the galaxy, it's possible that some of them are trying to communicate with us. However, if this is the case, they might be communicating in ways that we can't even comprehend. Their methods of communication might be vastly different from ours. So, what should we do if we ever encounter aliens? Many scientists believe that we should approach any encounter with caution. We should avoid making any sudden movements or aggressive actions, as these might be misinterpreted by the aliens. Instead, we should attempt to communicate in a peaceful and non-threatening manner. If we do make contact with aliens, it could have profound implications for our understanding of the universe. It could challenge our beliefs about our place in the cosmos and force us to confront some of the big questions about life, the universe, and everything. Now that we've explored some of the theories and possibilities of alien life, let's consider the idea of the Fermi paradox. This paradox asks the question, if there are so many intelligent civilizations out there, why haven't we seen any evidence of them? Why haven't we detected any signals or observed any spacecraft from other worlds? One possibility is that advanced civilizations tend to self-destruct. With technology comes the potential for destruction, whether through environmental damage, war, or some other catastrophe. It's possible that many intelligent civilizations reach a point where they are unable to sustain themselves and ultimately fail. Another possibility is that intelligent civilizations have no desire to make contact with us. Perhaps they are simply not interested in Earth or in communicating with other species, or perhaps they are too far away to detect our signals, and we are too primitive to detect theirs. Regardless of the reasons, the Fermi paradox remains a mystery and a subject of much speculation. But let's turn our attention to the possibility of life in our own solar system. While we haven't found any evidence of intelligent life, there are some promising signs that microbial life might exist on other planets or moons. For example, NASA's Mars rover has detected methane on the planet's surface, which could be a sign of microbial life. And scientists have found evidence of subsurface oceans on some of Jupiter and Saturn's moons, which could potentially support life. If we do find evidence of microbial life in our own solar system, it would be a major discovery and could have significant implications for our understanding of life in the universe. Let's consider the potential implications of discovering intelligent life. If we were to make contact with an alien civilization, it could have profound impacts on our society and our understanding of the universe. For one, it could challenge our existing beliefs and worldviews. We might need to reevaluate our ideas about our place in the cosmos. Our religious and philosophical beliefs, and our understanding of the origins of life. It could also raise questions about the ethics of interacting with other intelligent species and the responsibilities that come with such interactions. Another potential impact is on our technology and scientific progress. If we were to encounter a more advanced civilization, we could learn from their technology and knowledge, potentially accelerating our own progress. On the other hand, it could also pose a threat if the aliens have hostile intentions toward us. It's difficult to say for certain whether aliens, if they exist, would be dangerous to us. We have no concrete evidence of intelligent extraterrestrial life, and so any speculation about their intentions or behaviors is purely hypothetical. Some people argue that aliens could be dangerous if they are more technologically advanced than us and have the ability to conquer or destroy us. Others point out that any civilization advanced enough to travel through space would likely have a more sophisticated understanding of the universe and may be more peaceful and cooperative. It's also possible that aliens could be indifferent to us, simply observing us from a distance without any intention to interact with us at all. Overall, while it's fun to speculate about the potential dangers of alien life, the truth is that we simply don't know enough to make any definitive conclusions about their intentions or behaviors. The search for extraterrestrial life should be approached with an open mind and a healthy dose of curiosity rather than fear or paranoia. Regardless of the potential impacts, the search for intelligent life continues. We are constantly developing new technology and refining our techniques to search for signals and evidence of other civilizations. And while the chances of finding intelligent life may be slim, the pursuit of knowledge and discovery is a worthy endeavor in and of itself. We inhabit a galaxy known as the Milky Way, which contains hundreds of billions of stars. How did we arrive at this point, and what is our future? These concerns involve galaxies in every aspect. The known universe contains 200 billion galaxies, each of which is unique, immense, and dynamic. Where do galaxies come from? How do they work? What is their future, and how will they die? This is the Milky Way, our galaxy, approximately 12 billion years old. The galaxy is a vast disk with enormous spiral arms and a central nucleus. It is only one of countless galaxies in the universe. Galaxies are massive assemblages of stars. A typical galaxy could contain 100 billion stars. They are actually stellar nurseries, the locations where stars are formed and perish. The stars in a galaxy are formed in nebulas, which are concentrations of dust and gas. Our galaxy contains billions of stars, many of which have planets and moons orbiting them. But for a very long time, we knew very little about galaxies. A century ago, we believed that the Milky Way was the only galaxy in the universe. In 1924, astronomer Edwin Hubble altered the entire situation. Hubble observed the universe using the most sophisticated telescope available at the time, the 100-inch Hooker on Mount Wilson near Los Angeles. Far, far away, he saw hazy masses of light in the darkness of the night sky. He realized they were not even separate stars, they were entire star-filled cities, constellations far beyond the Milky Way. The astronomers received an existential jolt. We went from the Milky Way galaxy being the only galaxy in the universe to billions of galaxies in a single year. Hubble made one of the finest discoveries in the history of astronomy when he discovered that the universe contains a large number of galaxies rather than just one. This is the Whirlpool Galaxy. It comprises over 160 million stars and is characterized by two enormous spiral arms. In addition, the stars of the huge elliptical galaxy M87 shine with a golden hue since it is one of the oldest galaxies in the cosmos. And this is the Sombrero Galaxy. Its massive, bright core is surrounded by a cloud of gas and dust. All galaxies are very beautiful. They represent the fundamental building block of the cosmos. As they spin across space, they resemble enormous pinwheels. Galaxies are enormous on a grand scale. On Earth, we measure distance in miles. In space, astronomers use light years. This is how far light can travel in a year. Our galaxy's diameter is over 100,000 light-years, and we're now located at a distance of 25,000 light-years from its center. However, in the grand scheme of things, even it seems like a tiny dot. While the Milky Way seems enormous from Earth, when compared to other galaxies, it is actually rather small. Andromeda, the galaxy closest to us, is about 200,000 light-years wide, making it twice as large as the Milky Way. M87 is the largest elliptical galaxy in our own cosmic backyard and much bigger than Andromeda. But M87 is tiny compared to this giant, 6 million light-years across. IC 1011 is the biggest galaxy ever found. It's 60 times the size of our own Milky Way. It's common knowledge that galaxies are enormous and ubiquitous, but why is this the case? The origin of galaxies is a key mystery in astrophysics. Approximately 13.7 billion years ago, the universe began with what we refer to as the Big Bang, a period of intense heat and density. We know that there could not have been anything like a galaxy at that time, so galaxies must have come from that very early universe and formed from it. For stars to form and for galaxies to form from those stars, gravity is essential. After the Big Bang, the first stars began to emerge only 200 million years later. The earliest galaxies formed as their masses began to come together because of gravity. Thanks to the Hubble Space Telescope, we can now see the early universe when galaxies were just beginning to form. Numerous galaxies are visible to Hubble. The light we see from distant galaxies now, however, really departed those objects many millions or perhaps billions of years ago. What we see now is the distant past of those galaxies since it took so long for their light to get to us. The Hubble Deep Field reveals a collection of fuzzy dots that are quite different from the galaxies we see today. We can barely make out these little specks of light. Those fuzzy patches are actually millions or billions of stars beginning to come together. These barely visible blotches represent the oldest galaxies, which started to take shape around 1 billion years after the Big Bang. However, Hubble's range of visibility ends there. To travel much farther back in time, we need a different type of telescope, one too large to descend into space. This telescope could not only identify primordial galaxies but also trace their evolution. The evolution of galaxy and galaxy cluster formation can be followed, with all the galaxies that have developed since the cosmos was just a few 100,000 years old, leaving their imprints for us to observe. Finally, scientists can begin to answer the question, what did young galaxies look like? Galaxies have evolved from clusters of stars into the complex web of systems we see today, and this process is being observed by astronomers. As far as we can tell, the greatest structures in the universe today originated as star clusters, evolved into galaxies, formed clusters of galaxies, and ultimately coalesced into superclusters of galaxies. In the early galaxies, there was a lot of stardust, gas, and clumpy structures. However, modern galaxies appear organized and tidy. When and how did tangled clusters of galaxies become neatly organized spirals and pinwheels? Gravity is the explanation. Galaxies are shaped by gravity, and its effects determine their fate. At the center of most galaxies lies an unfathomably strong destructive gravity source, and our own Milky Way has one hidden at its core. Over 12 billion years have passed since galaxies first appeared. These stellar conglomerations may take many forms, from spirals to giant spheres of stars. However, there is still a great deal we don't understand about galaxies. How did galaxies evolve into their present forms? Did spiral galaxies always have to be spirals? The answer is almost certainly no. Young galaxies are a mix of stars, gas, and dust. They are untidy and chaotic. They begin as chaotic formations, like the Whirlpool galaxy, then over billions of years develop into more orderly forms. The Milky Way wasn't born from a single galaxy but from a cluster of several. Our Milky Way originated as a collection of disparate formations, objects of varying sizes and shapes that gradually merged to become the galaxy we see today. Gravity is what binds the various components together over time. It gradually draws stars closer, causing them to pick up speed and flatten out into a disk shape, with massive spiral arms gathering stardust and gas. This process has been carried out countless times throughout the cosmos. While visually distinct, these galaxies share the fact that they all seem to orbit the same central object. For a long time, researchers pondered what could possibly alter a galaxy's behavior, and they found out, a black hole, and not just any kind of black hole, but a supermassive black hole. The discovery of extreme amounts of radiation coming from the centers of certain galaxies was the first indication of supermassive black holes. In these galaxies, black holes are consuming their surroundings much like a giant Thanksgiving feast. The gas and stars are the supermassive black hole's dinner. Sometimes, black holes consume their food so rapidly that they spew it out into space as beams of pure energy. This phenomenon is known as a quasar, and the presence of a quasar indicates the presence of a supermassive black hole at the center of the galaxy. But what about the Milky Way? There's no quasar here. Does this rule out the existence of a supermassive black hole? Observing the motion of the stars is the key to finding the supermassive black hole in the heart of our Milky Way. Like the planets that circle the Sun, the stars also move due to gravity. What we discovered was a bizarre and violent environment at the center of our galaxy. Everything is more extreme, with stars passing one another at high speeds, unlike any other place in the universe. Photographs of the stars in orbit showed a remarkable phenomenon. They had to have been traveling at 1 million miles per hour or more. Only a gigantic black hole has the energy to toss large stars around like that. This curvature was the conclusive evidence for a supermassive black hole at the heart of our galaxy, as it is the black hole's gravity that drives the orbits of these stars. A massive black hole, measuring 15 million miles wide, sits at the heart of our Milky Way galaxy. So, is there any danger to Earth? We are in absolutely no danger of being sucked into our supermassive black hole. It's simply too far away. In reality, the distance between Earth and the supermassive black hole in the heart of the Milky Way galaxy is 25,000 light-years, which is many trillions of miles. For the time being, Earth is secure. Although supermassive black holes are the source of enormous quantities of gravity, they are not strong enough to bind galaxies together. In reality, the rules of physics dictate that galaxies should accelerate away from one another. So, what's stopping them? Because there's something stronger than a gigantic black hole waiting to be discovered. It is invisible and very difficult to detect. It's called dark matter, and it's everywhere. Supermassive black holes discovered by astronomers are found in the centers of galaxies and are responsible for the rapid movement of stars in their vicinity. However, they are insufficient to hold together all of the stars in a vast galaxy. So, what does hold them together? It was a mystery until a maverick scientist proposed that something unknown was in action. Fritz Zwicky, a Swiss astronomer, pondered in the 1930s why galaxies clustered together. He reasoned that because they weren't producing enough gravity, they should be flying apart. However, the force of our own gravity was insufficient, so he deduced that it must be something that had never been discovered before, something that had never even been considered, and he called it dark matter. Fritz Zwicky was decades ahead of his time, which is why he grated on the astronomical community. It was a brilliant idea, but he was correct. It's possible that individual galaxies are also held together by the mysterious substance that Zwicky dubbed dark matter. Galaxies rely on dark matter as a kind of protective framework that keeps them from collapsing and moving about. Now, scientists have discovered that dark matter does more than just bind galaxies together. It may have also triggered their evolution. Scientists believe that after the Big Bang, dark matter began to cluster, and these dark matter clumps eventually evolved into the nuclei of galaxies. However, the true nature of dark matter remains a mystery to physicists. Strange things happen with dark matter since we don't know exactly what it is. It's clearly not made of the same stuff that humans are. You can't push against it or feel it, but it likely exists everywhere. It's a ghost-like material that would pass right through you as if you didn't exist at all. Although our understanding of dark matter is limited, it appears to be abundant throughout the cosmos. This suggests that there is at least 6 times more dark matter than regular matter, the substance that makes up everything, including humans, in the cosmos. The way the universe functions seems to depend on dark matter. Recently, its existence has been indirectly detected in deep space through a process called gravitational lensing, which warps the light. The presence of dark matter can be tested using gravitational lensing. As a ray of light from a distant galaxy travels toward us, its path is bent around a large concentration of dark matter due to the latter's greater gravitational pull. Some distant galaxies indeed appear stretched and warped when viewed through the Hubble telescope. The distortion in the image is due to the presence of dark matter. By carefully examining the shapes and degrees of distortion of these galaxies, we can determine the density of dark matter. Now more than ever, the significance of dark matter to the cosmos is undeniable. It's what causes galaxies to form and prevents them from collapsing, even though it's invisible and undetectable. Dark matter rules the cosmos. These galaxies might seem isolated, and it's true that they are trillions of miles apart, but in reality, they exist in groups called clusters. These clusters of galaxies are linked together in superclusters containing tens of thousands of galaxies. The Milky Way's place in the cosmos remains a mystery. If you look at the bigger picture, you'll see that our galaxy is part of a smaller group of galaxies with about 30 members in total, with our galaxy and Andromeda being the 2 largest members of this group. Further observation reveals that our galaxy is embedded within the Virgo supercluster. Researchers are now creating maps of galaxy clusters and superclusters to better understand the cosmos. Galaxies are immense star empires, ranging in shape from enormous balls to intricate spirals. The problem is that they are always evolving. When we gaze into the cosmos, it's easy to assume that our galaxy hasn't changed in eons, but it has. The Milky Way is a dynamic galaxy, and its fundamental nature has been changing over cosmic eons. Galaxies don't just evolve, they move as well, and sometimes they collide with each other. When two galaxies collide, they merge over millions of years. This kind of collision happens all the time in the cosmos, and our own Milky Way is no exception. We are on a collision course with the Andromeda Galaxy, and that spells trouble for the Milky Way. At a speed of around 250,000 miles per hour, our Milky Way galaxy will collide with Andromeda in about 5 billion to 6 billion years. It will be the end of the Milky Way galaxy. If you could look out into space, you would see the entire Andromeda galaxy hurtling toward us at a tremendous speed. As the two galaxies interact, they will both become more and more distorted and closer together. There will be a dance of death between the two galaxies. Whenever galaxies collide, they eject clouds of gas and dust in all directions. As galaxies collide, their combined gravity will rip stars from their orbits and hurl them into the void. As we approach doomsday for the Milky Way galaxy, it will be a spectacular event. The two galaxies will eventually pass through one another and merge into a single galaxy. The Milky Way and Andromeda, as we know them, will cease to exist, and a new galaxy, Milkomeda, will be born. It will look like a completely new galaxy. There's no avoiding what's going to happen, but the question is, what does this mean for planet Earth? We might either be flung out into outer space when the arms of the Milky Way galaxy are torn apart, or we could end up in the center of this new galaxy. Stars and planets will be scattered all over the place, so this could very well be the end of planet Earth. Galaxies all over the universe will continue to collide, but this age of galactic cannibalism will eventually pass because there is an even more destructive force in the universe, a force that nothing can stop. It will eventually tear the cosmos apart by stretching everything to the point where galaxies are pushed apart from one another. Researchers have identified a new cosmic force. It's called dark energy. Unlike dark matter, dark energy has the opposite effect. It pushes galaxies apart instead of bringing them together. Dark energy, which we've only discovered in the last decade and which dominates the universe, is significantly more mysterious. We have no idea why it exists or what it's made of. We know of its presence, but beyond that, our understanding is limited. Dark energy is truly strange. Things resist and are pushed away from each other as if space itself contains tiny springs. In the far future, scientists predict that dark energy will overcome dark matter in the cosmos. When that happens, galaxies will begin to drift apart. Eventually, dark energy will cause galaxies to die off by accelerating the expansion of the universe, pushing all galaxies farther and farther away from us until they become invisible and move faster than the speed of light. At that point, everything else in the cosmos will vanish before our very eyes. However, the remainder of the cosmos won't disappear today or tomorrow, but it might in 1 trillion years. Galaxies will be left alone in the void. But this won't happen for a very long time. The cosmos is thriving right now, and galaxies are creating favorable conditions for life to exist. Without galaxies, I wouldn't be here, you wouldn't be here, and perhaps life itself wouldn't exist. This is unfortunate for us because the only reason life has evolved on Earth is that our tiny solar system was formed in just the right part of the galaxy. If we were any closer to the center, we wouldn't be here. Life in the center of a galaxy can be extremely hazardous. In fact, the proximity of our solar system to the galaxy's core would make it so radioactive that life would be impossible to sustain in any form. Being too far from the center would be just as bad. Out there aren't as many stars, and we might not exist at all. So, in a sense, we are in the Goldilocks zone of the galaxy, neither too close nor too far away, but just right. There may be millions of stars in the cosmic Goldilocks zone where conditions are just right for life. Furthermore, if our galaxy can support life, then other galaxies should be able to as well. The cosmos is vast, and the truly amazing part is that we continue to learn new things about it. Every time we think we've solved the problem, we discover that it's part of an even bigger one. That's incredible. Our Milky Way galaxy, and the galaxies beyond it, are full of mysteries and unanswered questions. Who would have guessed 20 years ago that we would be able to identify the black hole at the center of our galaxy? Who would have predicted 20 years ago that the astronomical community would accept the existence of dark matter and dark energy? We should feel astonished to be alive at this particular moment in cosmic history, on this particular planet, on the fringes of this particular galaxy. With the ability to ponder questions and seek answers across the entire cosmos. Galaxies are born, they evolve, they collide, and they die. The Milky Way is a fortunate home for intelligent life. Our fate is intertwined with that of every galaxy. Ultimately, our fate rests in their hands since they are the ones who created us and are shaping our identities.